You think a proton is made of quarks, three quarks held together by the strong force. Up, up, down. That's what textbooks tell you. That's the simple picture, and it's wrong. Or at least, it's so incomplete that it misses the most important fact about protons. A proton has a mass of about 938 MeV, mega electron volts. That's the energy equivalent of its mass. But here's what nobody tells you. The three quarks inside the proton, two up quarks and one down quark, have a combined mass of only about 9 MeV. 9 out of 938. The quarks account for less than 1% of the proton's mass. So where does the other 99% come from? It comes from energy, pure energy. The energy of the strong force field binding the quarks together, the energy of gluons, the energy of quantum fluctuations, virtual quark-antiquark pairs popping in and out of existence. The proton is not a collection of particles. It's a seething knot of energy, a bound state of quantum fields. And most of what you think is solid matter is actually empty energy. I'm Leonard Susskind, and I've spent 50 years thinking about quantum chromodynamics and the strong force. And I'm going to tell you what protons really are. Not the simple story, the actual physics. And it changes everything you think you know about matter. Let me start with the basic structure. A proton contains three valence quarks, two up quarks with electric charge plus 2, 3 each, one down quark with charge negative 1, 3, total charge plus 1. That's the proton's electric charge. These are called valence quarks because they determine the proton's quantum numbers, its charge, its baryon number, its spin. But these three valence quarks are not alone. They're surrounded by gluons. Gluons are the force carriers of the strong nuclear force. They mediate the interaction between quarks. And here's the crucial difference from electromagnetism. In electromagnetism, photons carry the electromagnetic force, but photons don't interact with each other. They're electrically neutral. Light beams pass through each other without interacting, but gluons are different. Gluons carry color charge, the charge of the strong force. And because they carry charge, they interact with each other. Gluons interact with gluons. This makes the strong force fundamentally different from electromagnetism. It's self-interacting, nonlinear, and this self-interaction has profound consequences. In quantum chromodynamics, QCD, the theory of the strong force, quarks carry color charge, red, green, or blue. These aren't actual colors. They're labels for the three types of strong charge. Antiquarks carry anticolors, and gluons carry color and anticolor. A gluon might be red antigreen or blue antiiod. 8 combinations total, 8 types of gluons. When a quark emits a gluon, its color changes. A red quark emits a red anti-blue gluon and becomes a blue quark. The gluon carries the color change. And because gluons carry color, they can interact with other gluons. A red anti-blue gluon can interact with a blue anti-green gluon. They can combine, split, exchange color. This creates a complex web of interactions, a seething sea of gluons inside the proton. And here's the key point. These gluons have energy, lots of energy. The strong force between quarks is incredibly strong at short distances. It takes enormous energy to pull quarks apart. This binding energy is what gives the proton most of its mass. Let me explain this with Einstein's E equals mc squared. Mass and energy are equivalent. The mass of a bound system is not just the sum of the masses of its constituents. It includes the binding energy. If the binding energy is positive, the system is heavier than the sum of its parts. If it's negative, as in most bound systems, the system is lighter. But wait, bound systems usually have negative binding energy. Atoms are lighter than the sum of their protons, electrons, and neutrons. Nuclei are lighter than the sum of their nucleons. This is called the mass defect. The binding energy is released when the system forms. It reduces the total mass, but the strong force is different. The way QCD works, the binding energy of quarks inside a proton contributes positively to the mass. The energy of the gluon field adds mass. The proton is heavier than the sum of its quark masses, much heavier. The quarks have a combined mass of about 9 MeV. The proton has a mass of 938 MeV. The difference, 929 MeV, is the binding energy, the energy of the strong force field. This is where the proton's mass comes from, not from the quarks, from the energy binding them. Now let me tell you what's happening inside the proton at the quantum level. The 3 valence quarks are not sitting still, they're moving. Exchanging gluons, the gluons create a field that binds the quarks. But because gluons interact with each other, the field is dynamic. Gluons emit and absorb other gluons. They split into quark-antiquark pairs. These pairs annihilate back into gluons. At any given moment, the proton contains not just 3 quarks, but a sea of virtual quarks, antiquarks, and gluons. This is the quark sea. Virtual particles popping in and out of existence on timescales so short they don't violate energy conservation through the uncertainty principle. The uncertainty principle allows virtual particles to exist briefly. Delta E times delta T is greater than or equal to h bar. If the energy violation is large, the time is short. Virtual particles borrow energy from the vacuum and pay it back quickly. They exist in a quantum superposition of being there and not being there. Inside the proton, the sea of virtual particles is dense. At any moment, there might be 4 quarks and 1 antiquark, or 5 quarks and 2 antiquarks. The number fluctuates. The only constraint is that the net quantum numbers match the protons. 3 more quarks than antiquarks. Total charge plus 1, but the composition is not fixed. It's a quantum superposition. The proton is not 3 quarks. It's a probability distribution over many possible quark and gluon configurations. Most of the proton's mass comes from the kinetic energy of all these quarks and the field energy of all these gluons. This energy, when you integrate over the entire volume of the proton, equals 929 MeV. That's the mass. That's what you're weighing when you weigh a proton, not the quarks, the energy. Now let me talk about confinement. Quarks are never seen in isolation. You can't pull a quark out of a proton. If you apply enough force to separate the quarks, something strange happens. The energy you put in creates new quark-antiquark pairs. Instead of freeing a quark, you create mesons, bound states of quark and antiquark. You never get a free quark. This is called confinement, and it's a fundamental property of QCD. Why does this happen? Because the strong force doesn't get weaker with distance like electromagnetism. In electromagnetism, the force falls off as 1 over r squared. Move twice as far, the force drops by a factor of 4, but in QCD, the force stays roughly constant as you increase separation, or even increases. This is because gluons interact with each other. As you pull quarks apart, the gluon field between them stretches. The field energy increases. Eventually, it becomes energetically favorable to create a new quark-antiquark pair from the vacuum. The field energy converts into particle mass. The new pair breaks the connection. You end up with 2 separate bound states instead of 1 free quark. The energy you put in doesn't free the quark. It creates more particles. This is why we never see free quarks. They're permanently confined inside hadrons. Protons, neutrons, mesons. Bound states. The strong force is so strong that breaking a bound state is impossible. You just create new bound states. Now let me tell you about asymptotic freedom. This is the opposite behavior at short distances. At very short distances, the strong force becomes weak. If you probe a proton with a high-energy particle, looking at scales much smaller than the proton size, you see quarks behaving almost like free particles. The force between them is weak. This seems contradictory. The force is weak at short distances but strong at long distances. This is the opposite of every other force, and it's unique to the strong force. It happens because of the gluon self-interaction. At short distances, the vacuum polarization from virtual gluons screens the color charge. This is anti-screening. It reduces the effective charge at short distances. David Gross, Frank Wilczek, and David Politzer won the Nobel Prize in 2004 for discovering asymptotic freedom. It's crucial for understanding QCD. At high energies, short distances, we can calculate using perturbation theory. The interactions are weak. But at low energies, long distances, perturbation theory breaks down. The force is too strong. We need non-perturbative methods. Lattice QCD, numerical simulations on supercomputers. This is how we calculate the proton's mass from first principles. Let me tell you about these calculations. Lattice QCD discretizes space-time into a four-dimensional grid, a lattice. Quarks live on the lattice points. Gluons live on the links between points. You write down the QCD equations on this lattice and solve them numerically. This is computationally expensive. It requires supercomputers, but it works. In recent years, lattice QCD calculations have computed the proton mass from first principles. Starting only with the quark masses and the strong coupling constant, they calculate the proton's mass. And they get 938 MeV, within 1% of the experimental value. This is a triumph of QCD. It proves the theory is correct. The proton's mass emerges from the dynamics of quarks and gluons, from the energy of the strong force field, not from the quark masses. The quark masses contribute almost nothing. If you set the quark masses to 0, the proton would still have most of its mass, about 900 MeV, almost unchanged, because the mass comes from binding energy, not from the quarks themselves. Now, let me connect this to the Higgs field. People often say the Higgs field gives particles mass. And that's true for fundamental particles like electrons and quarks. The Higgs mechanism is how quarks get their small masses. About 2 MeV for the up quark, 5 MeV for the down quark. But the Higgs doesn't give the proton its mass. The proton's mass comes from QCD, from the strong force, from binding energy. This means that most of the mass in the universe, most of the mass in ordinary matter, doesn't come from the Higgs field. It comes from QCD, from the energy of gluon fields inside protons and neutrons. You are made of atoms. Atoms have nuclei. Nuclei are made of protons and neutrons. And protons and neutrons get 99% of their mass from QCD binding energy. So 99% of your mass is not from the Higgs. It's from gluons, from energy. You are mostly energy, not particles. Energy bound by the strong force into structures we call particles. But fundamentally, you're made of fields, quantum fields. And the energy density of those fields is what we perceive as mass. Let me tell you what this means philosophically. Matter is not stuff, not substance. Matter is energy organized by fields. The solidity you feel, the mass you weigh, it's not because you're made of solid particles, it's because you're made of bound energy, quantum field excitations. The proton is not 3 tiny balls held together. It's a knot in the quark and gluon fields. A stable configuration where the fields are twisted together in a way that can't easily untangle. And this knot has energy, lots of energy. and that energy is what we call mass. When you hold an object, when you feel its weight, what you're feeling is the energy density of the quantum fields making up the quarks and gluons and the protons and neutrons and the nuclei and the atoms in the material. You're feeling energy, not particles, energy. This is the deepest insight of quantum field theory. Particles are not fundamental, fields are fundamental. Particles are just excitations, disturbances in fields, and mass is just energy density. Now let me address what happens when you accelerate a proton to high speeds. At the Large Hadron Collider, protons are accelerated to 99.9999991% the speed of light. Their kinetic energy is enormous. Each proton has a kinetic energy of 6.5 TeV, tera electron volts, thousands of times larger than its rest mass. When these protons collide, the energy is concentrated in a tiny volume. The quarks and gluons inside interact with enormous momentum transfers, and at these high energies, we see the quark and gluon substructure. The proton is not a single entity. It's a swarm of quarks and gluons. When two protons collide at the LHC, it's not a collision of two particles, it's a collision of two swarms. Individual quarks and gluons from each proton interact, and these interactions can create new particles. Higgs bosons, Z bosons, top quarks, whatever has enough energy to be produced. The energy of the colliding gluons and quarks gets converted into new particle masses. This is how we discover new particles, by smashing protons together and looking at what comes out. Let me end with what protons teach us about the universe. Protons are the most common baryon in the universe. Almost all ordinary matter is hydrogen. One proton, one electron per atom, and the proton's mass dominates. The electron contributes less than 0.1%. So the mass of the universe, the mass of all ordinary matter, comes from protons and neutrons. And the mass of protons and neutrons comes from QCD, from gluon field energy. This means the mass of the universe is mostly energy, not particle mass. Field energy, binding energy. The energy of the strong force. This is profound. It means the universe is not made of stuff in the way we intuitively think. It's made of fields. And the energy in those fields is what manifests as matter. The stars, the planets, your body, all of it is mostly empty energy. Quantum fluctuations of gluon fields inside protons. That's what you are. That's what everything is. After 50 years of studying quantum field theory, this still amazes me. The proton is not three quarks. It's a bound state of quantum chromodynamic fields. It's energy, confined energy, structured energy, but energy nonetheless. And that energy is what we call matter. Thank you for watching. Now you know what protons really are. Welcome to quantum chromodynamics.